All right, guys, welcome to day 2 of our review. Once again, I'm just going to go through a couple of problems to help you with the problems you're working on today. The problems I'm doing are not the ones that are on your sheet, but they are like those ones. Or sometimes I won't actually do a problem, I'll just give you some hints and suggestions for it. So let's go ahead and get started here. So for question 1, you want to be finding the limit of a complex fraction. The way that you find the limit of a complex fraction is by making the fraction no longer complex. So what do I mean by that? A complex fraction is a fraction that has fractions inside of it. And so what we want to do is we want to get rid of these little miniature denominators here. And so what we're going to do is we're going to multiply by the denominators to get rid of those things. So I'm going to multiply the top by 2 plus x. You could put it over 1 if you want. And since I'm multiplying the top of this big old fraction by 2 plus x, I also want to multiply the bottom by 2 plus x. Now we're not going to simplify the bottom part, but we are going to simplify the top part. So I'm going to distribute this in here like so. And as a result, I will end up with this. Oops. Okay, and what's cool about that is this piece right here equals 1 now. So I'm just going to make it a 1, and that was the whole purpose of that exercise, was to make it a 1. I'm also going to put this in parentheses, and I think I would encourage you guys to do that as well. It's helpful for remembering to distribute and stuff, because if you don't have those parentheses, sometimes we forget to do some operations that we need to do. All right, so but we still have a little denominator that we want to get rid of here. So guess what? We're going to do it again. I'm just going to multiply the entire top by 2 over 1 and the bottom by 2. All right, so we distribute in. So if I distribute there, 2 times 1 is 2. And if I distribute here, I'm just going to be putting the 2 there, right? And those are going to cancel. So all I'm left with is this. And now on the bottom, I have x times 2 plus x times 2. Okay, and then we're going to simplify from there. So first thing I need to do is I need to distribute this negative, and that's why those parentheses are helpful in that particular situation. So if I distribute that, I'm going to end up with the following: 2 minus x over x times 2 plus x times 2. And then these cancel out. So there they go. And a lot of times, guys, these steps will be exactly the same. You're going to multiply first to cancel out the denominators. Then you're going to simplify your numerator until you get it as simple as possible. And then the last step will be simply to reduce whatever you can. And as you guys can see here, we have an x on the top and an x on the bottom. So those just go away. And now I have the limit as x approaches 0 of negative 1 on the top. We have to put something up there. It can't just be blank, and it leaves a 1. And then we have 2 plus x on the bottom, as well as a 2. And then at that point, we could just do some direct substitution. So I'm going to plug in my 0. And when you do direct substitution, you can get rid of the limit symbol. So if I plug that in, I have 2 plus 0, which is 2, times 2, which is negative 1/4, is my final answer there. So that's how you handle finding a limit with a complex fraction. Now, something that's going to come up on your guys' problem is this kind of a situation. Okay, now over here, I had my x's cancel out. You guys are going to have something that looks like this, and these can cancel out, but they're opposites. A minus x and x minus a are almost the same, but they have opposite signs. And what do you get when you divide a number by something with an opposite sign that's the same number? Well, you get negative 1. So just keep in mind that whenever you cancel these out, it it doesn't just cancel out like I had. It actually creates a negative in the process. So you'll want to keep that in mind. All right, so that's it for question 1. Let's move on to question 2 here. The limit of g of x is equal to 5, and the limit of f of x minus 3 times g of x is 10, and our goal is to find out what f of x is. All right, well, I'm going to go ahead and apply my properties here. If I'm taking the limit of this entire expression here, I would apply the limit to all two of those expressions. So we're going to have the limit as x approaches 2 of f of x minus 3 times the limit as x approaches 2 of g of x. So these are limit properties that I'm applying here. Okay, whenever you're adding or subtracting limits, the limit applies to each piece separately. Also, when there's a constant in the front, you can just move it out to the front of the limit. So now I've just got this piece and this piece kind of separated now. And the benefit of that is that we know what one of those pieces are. We know that the limit of g of x as x approaches 2 is 5. So I could replace this whole thing over here with 5. Okay, so there's that. And then from there, we just got to do some basic math. The 3 times 5 here is 15, so I'm just going to replace that with 15. And then if we just add 15 on both sides, this cancels out, and then this side becomes 25. And so that would be my limit. The limit of f of x as x approaches 2 is 25, and that's what they wanted us to find. So the answer is 25. So the idea there is to go ahead and apply the limit to the pieces, each piece separately, and then replace those pieces with the numbers that they give you and find the missing one that you want. Okay, so that's question 2. Let's go ahead and take a look at question 3 here. Now for question 3, I'm not going to do a different example, but what I am going to do is I'm going to get you started on it, and then I'm going to give you a suggestion for what to do after that. In calculus, for the most part, and a lot of times we don't really like absolute values. For a lot of times we just change them into piecewise functions. And so here's the deal here with this guy. I want to rewrite this expression. All right, so the way that we rewrite that is we take the inside piece there and we set it equal to 0 and we solve for x. But in this case, x is already solved for, so x equals 0. Then you do a number line test and you pick a number to the left and you pick a number to the right and you plug it into the absolute value portion alone. So I'm going to plug in -1 for x, I'm going to plug in +1 for x, and you'll notice that this side, the absolute value of -1 changes. I'll put a C for changes into 1, whereas this side, the absolute value of 1 is 1 and there was no change. And that means that for all x that's less than 0, we're going to change the sign. And for all x that's greater than 0, we will not change the sign. And so this little expression here can be written in 2 different ways. Okay, let's go ahead and write this. Here we go. We have the fact that at x equals 0, it's 0. So I'm just going to put that one in the middle. But we know that for all x less than 0, we're going to rewrite this as x over -x, and that for all x greater than 0, we're going to write it as x over x. So for the one that is less than 0, we changed the sign. So you get rid of the absolute value bars and you put a negative in front of it. And for all x greater than 0, there is no change, so we just get rid of the absolute value bars and we don't change the sign. Now we're still not quite done yet here because we can simplify these. What does x over x equal? It equals 1. And so we would have -1 for all x less than 0, and 0, x equals 0, and then +1 for all x greater than 0. And so that's the first thing that you would need to do, is rewrite this expression like that. Okay, so changing piecewise functions, changing absolute value functions into piecewise functions is pretty helpful. Okay. You'll also, this is a pretty common setup too, by the way. Even if you don't have absolute values here, if you ever see one that says it's not equal to, well, that means that this one goes in the middle, and this other one here goes on the top and the bottom. It's just for the top, it's going to be less than 0, and the bottom, it's greater than 0. So that's pretty common. But the changing of the signs thing we had to get from absolute values. So now the other thing I want to point out to you guys in order to complete number 3 is that you need to remember that for a piecewise function's limit to exist at the junction point, that's this number over here, we're finding the limit at 0. In order for the function's limit to exist at that junction point, the limit from the left and right have to match. So these would have to match. Okay? If they do, then that's the limit. If they don't, then the limit doesn't exist. And so I'll leave that with you guys and let you finish it. We're going to be skipping question 4. The answer is D, so just go ahead and pick it and move on. And we're going to be skipping number 5 as well. The answer is B, so skip it and move on. And we're going to skip number 6. The answer is D. All right, and for question 7, I'm just going to refer you guys back to question number 10 from our last lesson on Monday, or whatever day it was. I would look at that one because it's basically the same kind of question there. All right, let's go ahead and take a look at question 8 here. What we're doing on this problem is we're finding the limit of a composite function. A composite function is a function that looks like this, where you have one function being plugged into another function. In this case, it's a function being plugged into itself. Okay, now the way that you find the limit of a composite function is by taking your limit and applying it to the inside function. So really what we want to do here is we want to find the limit of f of x as x approaches 4. Now what's interesting about this question is that they're giving you two different representations of the function. They give you an equation or they give you a graph. Now the equation for the first step is a little bit more work if you try to use the equation. It's easier to use the graph to find this limit here. However, in the second step, you can't use the graph because you'll see why in a minute. And so we have to use the equation. But at that point, using the equation is not that hard. Now, let me just kind of show you some, really you don't need the graph at all. You could do the whole thing with just the equation. So one way that you could do this is to find the limit of this function as x approaches 4. Notice that 4 is the junction point. That's where the pieces are seeming to be connected together. To find a limit of a piecewise function at a conjunction point, you need to find the limit from the left of your junction point, and you need to find the limit from the right of your conjunction point. So basically, you could just plug 4 in here and here. If they come out to match, if this one gives you the same answer as this one when you plug in 4, then that means the limit exists, and that's what the limit is. Okay. The other option for this one is just to look at the graph. What is the limit as x approaches 4? Well, here's where x equals 4. And the limit is going to be the dot that it's being approached as we go from left and right. And as you guys can see, they're landing here at this open dot. And so that limit there looks like it would be negative 11. So I like the graph more, but you would get negative 11 also. If you plugged in 4 up here to the top, you'd get negative 11. And if you plugged it in the bottom piece, you get negative 11. And therefore, that means the limit is negative 11. So we get negative 11. Now, on the second half of this process, though, we need to figure out what is f of negative 11 now, because I just figured out that this inside piece equals a negative 11, so I replaced it with negative 11. So now I need to find what is f of negative 11. Well, you can't do that on the graph because, as you guys can see, our x-axis only goes to x equals negative 4. It doesn't go out to negative 11, so you can't use the graph for the next half of this problem. We have to use the equation. Now, when it comes to a piecewise function, you have to look at your x value that you want to evaluate. I want negative 11. Well, is negative 11 greater than 4, equal to 4, or less than 4? Obviously, it's less than 4, so that means we're going to be plugging the negative 11 into this piece here to get our final answer. So that's negative 11 squared minus 3 times the negative 11 minus 15. And so negative 11 squared is 132. Negative 3 times negative 11 is 33. and then we minus the 15. So at this point, it's kind of just basic math stuff, but what the heck, I guess we'll go ahead and finish it. Wouldn't it be funny if I got an error on my basic math after saying that? Looks like it's going to be 150 to me. All right. Anyway, so that would be the final answer there. But a couple of ideas there is that the big idea here is that when you have a composite function, you apply the limit to the inside function. You find that limit, and then whatever you get, that's what you're going to evaluate the outside function at. On this problem, though, we had the dilemma of working with two different representations. In the one case, one is easier but limited, whereas in the other case, this one's a little bit more, process involved, and yet it works all the time. So let's go ahead and move on to number 9 here. I'm going to say go back and look at that same question 10 if you haven't already done so on our first multiple choice part A video from this week, our last lesson. We went over something like that already. Now, question 10 has a lot going on, so I'm not going to do any examples for you, but I will give you some hints on it. It's not so much that these are things that we haven't talked about. It's really just the fact that they've crammed a lot into one single question. And so here's one thing to keep in mind. The first thing we're going to need to do is you're going to need to rewrite it. Remember when I said that if you have x is not equal to 2, well, that's the same thing as saying x is less than 2 and x is greater than 2. If x is everything that's not equal to 2, that means it's all the numbers less than 2 and all the numbers greater than 2. And I like writing it like this better for the stuff that we do in this class, okay? Whereas the x equals 2 part, that just goes in the middle. So that would be my first suggestion, is to rewrite it like that. The next thing is you're going to need to factor and reduce the rational expression if possible. You guys do have on this problem something like, I don't know what the numbers are. I'm just going to make up a problem real quick, but you have something like this. I don't know. And the goal here is you're going to need to factor the top and see, can you cancel that out with the plus 2 after you factor it? So do that. It may not factor. And then you're going to find the limit of f of x as x approaches 2, and you're also going to find f of 2. Now, how do you find the limit of your function as x approaches 2? Well, whenever you're approaching the junction point, to find the limit, you find it from the left and you find it from the right, and if they match, then the limit exists. How do you find where f of 2 is? That's the one in the middle here. That's where x actually equals 2. You're not approaching from the left and the right. You're actually doing that. So for this one, you plug it into the middle piece. For this one, you do the top and bottom and make sure they match. So if these two things match, if the limit exists and the function exists and they are the same, then we could say that that function is continuous. Okay. Next, if the limit exists, but in other words, if the limit exists, in other words, this piece matched this piece, but it's not equal to the middle piece here, then the function is no longer continuous. Okay. In that case, though, when you have a function where the limit exists, but it's not continuous, we call that a removable discontinuity. Anytime the limit exists, but it's not continuous, that's a removable discontinuity. Those are things where you have like a hole or a hole with a dot. If the limit exists, meaning as we approach from the left and the right, they both are meeting at the same spot, that's the open dot. But the point that actually exists is not there, it's somewhere else, then that's a removable discontinuity. Or it could be that the function itself doesn't even exist there, but that's still a removable discontinuity, even if there is no dot. Okay, so we have two situations. If the limit exists, in other words, the top piece and the bottom piece are equal, and the function exists, which is this middle piece, and those two things are the same, then it's continuous. But if it turns out that the limit exists because the top piece and the bottom piece are the same, but they're not the same thing as the middle piece, then that would be a removable discontinuity. Now let's continue on. The other scenario is let's say you're trying to find your limit and you find out that the limit from the left and the right are not the same. In other words, when you plug into the top piece and the bottom piece, they don't come out to be a match. Well, in that case, you have a jump. Maybe your top piece ends up at y equals 3, but the bottom piece is ending up at y equals -2. And with that case, you have a jump discontinuity, and that would be a jump. So the problem is asking you guys to determine, is this a jump discontinuity? Is it a removable discontinuity? Or is it continuous? So it's continuous if this happens. It is removable if this happens. And if the limit on the left and right are not the same, then it's a jump. Okay. Now there's one other possibility. The other possibility is if this last one here that I've already brought up, if neither the left nor right hand limits exist, then it's a vertical asymptote. Okay. So remember I told you back on this step here, you want to factor and reduce it. Well, if it doesn't reduce, then it's probably a vertical asymptote. In other words, if you try to plug it in, you just get something that doesn't make sense, like a 0 on the bottom, and it wasn't factored out, then it's a vertical asymptote. Okay, so we have those three outcomes. First of all, you want to rewrite it this way. Factor and reduce if possible. If it's not possible to reduce it, chances are it's the vertical asymptote situation. But if it does factor, then if the limit exists and the function exists and they're the same, it's continuous. If the limit exists but it doesn't match the function, then that's a removable discontinuity. If the limits on the left and right are not the same, but they exist, then it's a jump. Okay, so those are our outcomes there. All right, let's go ahead and take a look at question 11. Let's talk about the types of discontinuities and what they look like on a graph, because that's all you really need to do in order to answer this question. There are two types of removable discontinuities. In other words, discontinuities where even though the function is not continuous, the limit still exists. So you could have a situation where there's a hole, that's this, or you could have a hole with a point. Those are the only types of removable discontinuities that we can think of. There are two types of non-removable discontinuities. You have the vertical asymptote situation, which looks like this, or they could be going the same way, like they don't have to both be going opposite directions. They could be going the same direction, but the point is there's a vertical asymptote. Or you have a jump situation where there's just a clear break in the line and they're just two completely separate pieces that don't connect. That would be a jump situation. And so that's what you're going to need to be aware of those things in order to answer question 11. All right, let's go ahead and move on to question 12. I would say, once again, look back at the same notes for question 11. You should be able to do it at that point. Question number 13. For this one, I will help you turn the words into a picture, and that should help you be able to determine the answer. So here's what they say. If the limit of f of x as x approaches 6 exists, with that limit value being less than 5, and f of 6 is equal to 10, which of the following statements must be false? All right, so to draw this graph, first of all, notice that we're approaching x equals 6. So as I'm drawing my graph here, we want to go out to 6 on the x-axis. Now, it says that the limit exists, which means that it's either continuous or there's a hole with a dot or just a hole. Because if the limit exists, it's either this situation where you have a hole, because a limit exists there, or it could be this situation where you have a hole with a dot, or it could be this situation where you have just a continuous function where the dot and the hole match. Okay. Now, what they're telling us also is that at the limit at x equals 6 has to be less than y equals 5. So I'm going to go up 5 on the y-axis. You'll notice that, how do I know this is a y? Well, it's just part of the definition of a limit. This is the x value and this is the y value. So the y value of the limit, in other words, this dot right here, would have to be less than 5. So it's got to be below this upper line here. So now that's the part where it gets confusing, because it doesn't tell you where it is. It just tells you it has to be less than that. So you could draw your dot here. That's below 5. You could draw your dot here. You could draw your dot here. You could draw it anywhere so long as it's below 5. So it doesn't really matter which one you pick. I'm just going to pick, like, let's just do this one down here. Why not? So that's less than 5. So the limit exists. So I know that from the right and from the left, they have to meet at that point, okay? Now they're telling me, though, that f of 6, the actual dot at x equals 6, has to equal 10. So that's 6, 7, 8, 9, 10. So as you guys can see, we do have the, oh, I just realized I put my graph in the wrong spot. X equals 6 is over here, so let me move it over a little bit. My bad. Sorry. Anyway, f of 6 equals 10. So the actual dot when x equals 6 is at 10. So 6, 7, 8, 9, 10. So we're going to have a dot up here. So there's my graph. So the complicated part of this is turning these words into a picture. Knowing that the limit exists, I knew it had to be one of these types of pictures. And then understanding this tells me that that dot, whether it's this situation, or this situation, has to be below 5. Although here it's a little bit confusing. Let me redraw that one. The limit has to be below 5. In other words, this guy. The dot can be here or here. It doesn't really matter. But the limit has to be below 5. So I know my open dot has to be somewhere underneath y equals 5. And then finally we have our dot, which is up here. Okay, so that's one way to draw the graph. But just understand, since the limit as x is less than 5, the limit as x approaches 6 is less than 5, that's not the only way to draw this graph. I mean, this graph could look like this. Well, not that. It's got to be a little lower, like maybe like this. You could do that because it's still, the limit exists. It's still less than 5, and this dot's still up here. So it doesn't really matter how you draw it. So there's some wiggle room here. And that's why one of the questions says must be false. Okay? Which of the following statements must be false? In other words, there's no way you could possibly draw the picture so that that statement works. So these questions are kind of tough because they make you think of a lot of possibilities, but they're good for thinking. So there you go. Let's go ahead and move on here. Let's take a look at question 14. How to determine if a piecewise function is continuous, and if it isn't, how to explain why. All right, so how do you tell if a piece, because this question basically has to do with explaining if a piecewise function is continuous or not, and then explaining why if it's not. So when you have a piecewise function, you need to do 3 things to see if it's continuous. You need to find f of your junction point. You need to find the limit as x approaches your junction point from the right. And you also need to find the limit as x approaches your junction point from the left. And just so you guys know, this means you're going to use the piece where it's greater than c, and this means that you're going to use the piece where x is less than c, and this means you're going to find the place where x equals c. Okay, now if you find all 3 of those and they are all the same, then it's continuous. Okay, then it's continuous. Now, if you ever have a situation where these 2 are not equal, then in that case you would say the limit does not exist. And the way that you would write that is you would say, well, the limit as x approaches c from the right is not equal to the limit as x approaches c from the left. Okay? Now, let's just say that these 2 things are equal to each other. That means that the limit exists. So anytime these 2 pieces are equal to each other, that means the limit exists. But let's just say that even though those 2 things are equal, the value of the function is not equal to those. Oh, I put that in the wrong spot. My bad. Back up. That was supposed to be over here. So the actual function value doesn't equal those things. In that case, you would say the limit does not exist again. I'm sorry, no. Sorry, my bad. You would say it's not continuous because the function is not equal to the limit. So even though the limit exists, and even though the function exists, they're not the same thing, and therefore it's not continuous for that reason. So both of these are situations where it's not continuous, the middle piece. So in this case, if the limits from the right and left-hand side are not the same, then the reason the limit doesn't exist is because of this right here. But if you ever have a situation where the limit does exist, but it doesn't match the actual function at that point, we would say it's not continuous because the function is not equal to the limit at that point. There is one other final situation that can occur. Sometimes you'll come across a piecewise function where it looks something like this. We don't really care what's here right now, but let's say you have something like this. In that case, you would say that the limit doesn't exist. I'm sorry, not the limit. My bad, I keep saying that. It's not continuous because, do you guys see something funny about this? There's no equal sign anywhere. Sometimes they'll put the equal sign here. Sometimes they'll put the equal sign here. Or sometimes they'll sneak the equal sign as just a whole separate piece. But there is no equal sign anywhere. And that means that f of c does not exist. So if you ever come across a situation where there's just no equal sign, that's another situation where a piecewise function may fail to be continuous. So we have 4 different scenarios. No equal sign means the function doesn't exist. Back up a lot here because I want to bring up everything else I had a second ago. Bear with me. There we go. Or you can have the situation where the limit exists and the function exists, but they're just not the same. That's another reason why it would not be continuous. Or you could have a situation where the left and right-hand limits don't match, and that means the limit doesn't exist. That's another reason why it would be not continuous. But if you find the function, the limit from the right and left, and all 3 are equal, then it's continuous. And the way you would explain that is just by stating this stuff right here, just writing all that out. That would be good enough. Okay, so that's how you show your work, and that's how you determine the answer as to whether it is continuous or not and why it's not. Okay, let's go ahead and take a look at question number 15. How to show a piecewise function is continuous. You're going to want to see question 14 again because I went through all that already. But once again, you need to rewrite this. Okay, you need to rewrite this to begin with. So first of all, anytime you guys see this not equals to thing, I would say we're going to change that into this situation. We're going to take this one and put it in the middle. And then not equals to 3, well, that could be anything where x is less than 3 or x is greater than 3. So we're going to split it up like that. And since that function goes with both of those, it goes on the top and the bottom. Now, another thing to keep in mind here is that it may be possible to reduce these fractions here. Okay, you're going to factor it. So let's do that. If I were to factor this, what would it be? Let's see. It may not factor. If it doesn't factor, then that's all right. But it does factor. So if I factor this, it looks like this, and so therefore these go away. And so the best way to rewrite this would be to write it, instead of leaving it like this, we put the reduced form, which is just x plus 4. And so that's how I recommend rewriting question number 15 before you begin answering the question. But like I said, after you rewrite it, just look at what we did in question 14. That'll answer the rest of it for you. All right, so that ends it for the day. Hopefully it was helpful. We will see you guys later. Bye-bye.